I want to talk a little bit about the National Academy of Sciences study, sort of the background there, how TIAX got involved with that. Then I want to summarize those results really briefly to put it in perspective from the U.S. side of things, and then try to extend using sort of, as Drew said, using the same methodology we used on the NES study, extend those results to Europe, and then finally give you some closing remarks. Next slide, please. So let's go through the NES study. This was a study that was legislatively required by our Congress to engage NHTSA, which is to engage the national academies to develop a report that evaluated both medium and heavy-duty vehicle fuel economy. And that was in the Energy Independence and Security Act of 2007, ESA. It also required NHTSA to conduct its own study on fuel efficiency of commercial, medium, and heavy-duty on-highway vehicles and work trucks leading up to their rulemaking. And then rulemaking process was a joint effort between NHTSA for fuel economy standards and EPA for the greenhouse gas standards. The committee, which was an assembly of experts ranging from people that had heavy-duty engine experience and vehicle experience, to hybrid experts, to experts on moving fuels, logistics, moving goods, as well as end users that actually use these technologies. The committee's objective were to conduct an assessment and develop a report, and that assessment was to include not only the technologies, but also their costs, to analyze potential technologies that may be used practically to improve medium-duty and heavy-duty economy. These bullet points were taken out of the legislation, so there is a little bit of duplication here, but this is what the legislative intent was for the committee. Analysis of how such technologies may be practically integrated into the medium and heavy-duty truck manufacturing, assessment of how such technologies may be used to meet fuel economy standards, and finally associated costs and other impacts on the operation of medium and heavy-duty trucks, including congestion. We were retained by the committee to provide a comprehensive set of fuel savings technologies, their benefits, and price. So our scope was really limited to those technologies that could be used on the vehicle as opposed to things like logistics, and I'll get into that in a second. So what we tried to do was develop detailed forecasts of fuel consumption reducing technologies, supported evaluation of the medium and heavy-duty vehicle technologies by researching the technologies and their costs through extensive interviews of manufacturers, fleet owners, and others to produce a detailed matrix of related technologies and vehicle types over time. And really the value add here was really the work with the manufacturers, to go interview the manufacturers, get their input into this. What is practical? What is reasonable in terms of estimates of fuel consumption benefits? What are reasonable in terms of the cost? And I think that process helped quite a bit in terms of buy-in from the industry of the ultimate development of the regulations. We also developed a detailed matrix of fuel-saving technologies, their fuel consumption benefits, and costs. And the focus was really sort of near-term, 10-year time frame, and of that scope, we also visited many, many specific sites. Next slide, please. So our approach really focused on the technology part of this. So identify the technologies, estimate the consumption benefit, and then come up with cost estimates. We did not break down in great detail what the estimates of the cost price are, nor did we do an analysis of the manufacturing process, nor did we do an analysis of operation and maintenance or life cycle costing. We did include some estimates on productivity, fuel consumption benefits, and a brief discussion of some of the enabling technologies. But again, it was did not include any detailed analysis, cost analysis, infrastructure analysis, or the policy landscape associated with increased use of longer and heavier vehicles. Similarly, with operation and logistics, we did look at such technologies as on-vehicle optimization tools, for example, driver training, telematic navigation, those sorts of things, but did not look at any off-vehicle, off-fleet optimization tools or any optimization of the good movement process at all. This is really technology-based on the vehicle. Next slide, please. So where do we get our major sources of information and data? We had site visits to all the major truck engine and manufacturers, included Cummins, Daimler and Detroit Diesel, Navistar, Kenworth, Peterbilt, and Volvo. We also went to the suppliers, tier 1 suppliers like Allison, Arvin, I guess it's Meritor now, Zur, Eaton, Great Dane, and ISE. So part of that was looking at the hybrid equipment manufacturers and what systems they had. We also had one visit with a fairly progressive end user, Walmart, and we did attend one conference at the University of Michigan, and then there was other meetings that occurred at some of the committee meetings, Conway, the Aluminum Association, as well as we went to several of the testing organizations, ARC from an aerodynamic point of view and TRC from a road testing point of view. And of course that was all supplemented prior by doing literature review of journal articles and research reports, including what our Department of Energy had done relative to technology, NAS committee presentations, 21st Century Truck Partnership, and a number of company data sheets, press releases, etc. And we tried at times to extend the results of previous studies to other vehicle classes, adjusting for factors such as duty cycle, vehicle weight, and engine size. And I might just pause there for a second and say that there was a number of studies that TIAX had taken on before this study, including I think one that is given in the back there, reducing heavy-duty long-haul combinations, so tractor-trailer studies that we worked with Southwest on. They give us some background relative to this study. We also performed a study on retrofit of aerodynamic devices for trailers, tractors and trailers in the California setting. So let me summarize real briefly some of the results of the NAS report. So our scope included Class 2B, which are large pickups, vans, all the way up through the Class 8 tractor-trailer. We did this on a vehicle-by-vehicle basis as opposed to trying to look at it individually, all the particular vehicles. We realize that the heavy-duty market is a very complex market, has many, many different vehicles, has many, many different applications. But to get an idea of what is possible, we picked these particular vehicle classes. And we tried to include all the technologies we could think of. The broad categories include aerodynamics, improvements in engines, tires and wheels, weight reduction, transmission, driveline, hybridization, driver management and coaching, and anything that you could do relative to idle reduction, which might have been incorporated in some of the hybrids. We also looked at technology attributes, trying to make sure that we could describe the technology. What is the baseline that we're comparing against? What is the fuel consumption benefit? Trying to come up with a good estimate of what the cost would be, retail price, when it could be introduced, and then the effect of that technology if it was an improvement on weight, coefficient of drag, etc. So just to give you an idea of the complexity of this market, you can see that there are all very different vehicles going from on the bottom left here of a heavy-duty pickup truck, all the way up to the tractor-trailer, and then, of course, the buses, 40-foot transit bus, intercity, or the over-the-road motor coach. There's many opportunities to reduce fuel consumption, but as you can see in this chart, regardless of what the class of vehicles are, the energy losses from the engine, the aerodynamics, and the tires dominate. Gearbox are there, axle is there, electric accessories are there, maybe a little bit more on the bus side of things, but mostly the amount of energy losses occur in the engine or due to the fact that you have to push that truck against the forces, the aerodynamic forces, or overcome the inertia forces. So the real challenge then is how can you reduce or improve the efficiency of those systems in order to reduce the fuel economy. This is a roll-up of our results for the NES. And big picture-wise, you could see that the types of reductions that we could get here are about 50% fuel consumption benefit across the board. Now, that said, the vocational applications, box truck, bucket, refuge, and to a certain extent, bus, all those that have a duty cycle that is dominated by stop and go, hybridization shows the biggest benefits. You can get some of those benefits in the light duty side, the 2B side, and we've also shown that you could get some of the benefits of hybridization on the tractor trailer with the system that we looked at. Aerodynamics dominate for those vehicles that are operated on the highway type drive cycles. So tractor trailer would be fairly high, coach would be fairly high. Light duty is lower, but again, they've done a lot of work on proving on aerodynamic body shapes there. So the engine you can see is in red here, and that has throughout any application has a fairly large chunk. And then tires, weight, light weighting, tires and wheels, transmission are much smaller. And then management and coaching we found made the most sense on the tractor trailer, not much on the other applications. Go to the next one, Peter. This shows the trajectory of costs, percent benefit on the y-axis, package cost on the x-axis, and the outlier here in terms of the cost curve is the light duty. So the light duty seems to have a considerable amount of benefit for cheaper cost. Maybe that's not surprising considering that's a mass market. Interestingly, the trajectories of the rest of the applications are closely bundled together, which gives you some credibility relative to the costing and potentially how it could be implemented. And then, of course, as you get, there are least cost effective technologies that are included in this, and you can see how that works as you get out further into the package cost and not much benefit. Next chart, please. I'm not going to go through this, but I'll leave this in the presentation, but this is just the details that were provided in those two previous charts. So you can see that, for example, on the tractor trailer, with an adjusted fuel consumption by subtracting off the added weight that is associated with some of the fuel savings technologies, you're near 50% fuel consumption benefit, albeit at a cost. So what were our major conclusions of the NES study? One is that you could get near 50% reduction in fuel consumption in the 2017 timeframe. The baseline vehicles that we were talking about here were model year 2008, 2009 diesel, and model year 2008, 2009 gasoline. So the NAS study was using 07 compliant, US 07 compliant baseline. And I'll bring this up again. That was EGR with a DPF. That's different than what you're going to have here, and we'll talk about that in a minute. Sort of a top line, two top line things that we sort of came out after talking to many of the manufacturers was that there's no reason trucks need to idle anymore eventually with the hybridization and electrification of the platforms. And secondly, which it seems like Europe already has, but the U.S. should have some sort of maximum speed limit that could be hardwired into the trucks for a number of reasons. One, the technology is there. Two, it at least unifies one of the variables in terms of truck specification, which is already very, very complicated. Next slide, please. All right, so now what I wanted to do was take that methodology and extend it to Europe. And what you see on this slide is the EU vehicle segmentation and the GHG emissions by segment. And this is out of a report that was done for the Commission by AEA Ricardo. And getting these kind of numbers is a lot of work. So they did a really good job of trying to put all this together. But you can see that the service sector here, in their definition, the service sector went from 3.5 metric ton vehicles all the way up to 7.5 metric ton vehicles. Equivalent class in the U.S. might be Class 2B. And you can see that the fuel consumption that we have in the U.S. is about 13% of the total, whereas the GHG emissions were estimated at about 13%. Pretty comparable. And you can go through the rest of this, like, for example, you get the long haul and regional delivery. That looks like it's about 51% if you combine those two, whereas the tractor-trailer type applications in the U.S. are doing about 61%. So I conclude in looking at this stuff, except for the buses and coach, and not surprising, the U.S. Use of those transit modes is not very good. Except for those two options, the rest of the market looks very, very similar, at least in terms of fuel use and how it divides up between the various segments. Next slide, please. However, there are big differences in what happens in the vehicles here in Europe versus the U.S. And in the next couple of slides, I just kind of want to walk through some of that a little bit. Obviously, the cab over design dominates here compared to the conventional in the U.S. Two examples are shown here. Tractor characteristics, width pretty much the same, height pretty much the same, length a big difference. Much stubbier in configuration in terms relative to the sleeper type cabs that are used in the U.S. Frontal areas looks like it's about the same. The majority of the tractors, at least according to the AEA study, are 2 axles, whereas the majority in the U.S. are 3 axles. So that reduces the number of tires as shown. And the driveline configuration is nominally a 4x2, whereas in the U.S. it's a 6x4. And then weight, considerably different between the two vehicles. From a fuel consumption point of view, the driveline configuration ought to be better. Weight obviously will help too in terms of reducing the fuel consumption. Next slide, please. If you look at the trailer characteristics, the big difference here is in length. Although the kingpin distance is considerably different, which might tend to help relative to the gap between the tractor and trailer, which would help reduce some of the aerodynamic losses. Number of axles, again, 3 typically in the EU versus 2 in the US. Number of tires goes down. Tare weight of the trailers is a little bit lower, especially with curtain side trailers. Payload's probably about the same. Total vehicle weight about the same. Major difference in terms of overall length of the vehicle. 16.5 compared to the US, which would be in the 23 meter length. Next slide, please. Just to look at some other factors that would affect fuel consumption here. Drag coefficient. US sort of best technology right now is in the 0.62, 0.64. I don't have any data, but it would be nice to know what the manufacturers here say. I speculate that the EU, the cab over designs could be better. But I would say, you know, in our analysis here, we assumed it to be the same. Trailers are obviously different. The engines are comparable. There seems to be more of the automated manual, the AMT used here in Europe versus the typical 10-speed manual still in the US. Speed, obviously a huge difference relative to the US versus the EU. Weight's about the same. Fuel consumption, I'd say it's a little bit better here, and I'll have some explanations of why that might be the case. And then, of course, a major, major difference is fuel price, right? We're running at about 0.75 euros per liter. Here it's about $1.35 euros per liter. So there's obviously a driver in terms of the marketplace to bring in fuel consumption technologies, and maybe this is one of the explanations too of why the European market has better fuel economy than the US market. Next slide, please. I borrowed this slide from Daimler. Long-haul fuel economy has improved and held relatively constant with increasing emission regulations here. So you can see this dates back to 1965, where you guys were in the 50 liters per 100 kilometers, you know, coming down into the low 30s in the 2010 timeframe. I've shown where the U.S. fleet is at 6.5 miles per gallon, so 39 to 36 liters. The trend is that you guys are lower than in Europe than the U.S. Next slide, please. One of those explanations is the emission reductions that occurred in the U.S. versus the EU. This chart shows the red and the black are the PM and the NOx regulations in the U.S. The diamond dots are the brake thermal efficiency. So you can see as we went from electronic controls to improving turbo efficiency, increasing injection pressure, increasing cylinder pressure, all that increased the brake thermal efficiency of the engine. We took a little of that away when we had the consent decree, which occurred in 2002, where EGR was required, and then further in 2007, where you actually had to push the EGR even harder and add the DPF. 2010, the experience is with the SCR added system to this, where you can increase engine out NOx, decrease engine out PM. You have actually increased the efficiency from the 07 product line. In Europe, you guys were more fortunate. You didn't do the DPF EGR step. So I would say your curve would probably stay more higher on this, although now Euro 6 is coming with the DPF, but presumably the manufacturers have learned a lot from the US experience here and will be able to mitigate most of that. Interestingly, as you go to onboard diagnostics and improve controls, and you can tune the SCR DPF systems to the applications, then most manufacturers were projecting an increase in efficiency. And then waste heat recovery is the next step, followed by advanced engine concepts, vehicle electrification, taking the accessories off the vehicles. So this is one view, sort of a composite view of our talks with the engine manufacturers on where they could get. Obviously, the dotted line is not there yet, and there's a heck of a lot of work that has to be done in order to get there, but it's possible. Next slide, please. This shows the technologies that we applied in trying to see for the vehicles that we evaluated in the EU, what sort of reductions you could get on a vehicle-by-vehicle basis by applying fuel savings technologies. And let me first state on the aerodynamics, we really only looked at the trailer in most applications. although we did look a little bit in some of these, like the urban delivery straight trucks, where some of those don't have cab or streamlining kind of technologies. We looked at lightweighting throughout. We looked at automatic tire inflation for some of the technologies, some of the applications. Low rolling resistance tires, especially on some of the high, the low rolling resistance wide base tires on some of the highway type based vehicles. Transmission and driveline included aggressive shift logic, early lockup, increased transmission gears, transmission friction reduction, but that you have to be a little bit careful with that when you start putting in the hybridization too. And then engine efficiency across the board for all market segments. And then hybridization, we looked at a number of different possible ones. The dual mode hybrid system is one that Marvin has put in. It's the equivalent sort of a Toyota type system. Parallel hydraulic hybrid, and then series hybrid. And then management predictive cruise control. So when we did all that and applied it with the same methodology, let's go to the next slide. Let me just, before I tell you what the results are, this just kind of gives you a technology roadmap for how we looked at how the engines, the larger size engines, are going to improve. So what is shown here is where we were in 2007, which was the baseline for the NAS, going up to the 2015-2020 package. And there was continuous improvement in terms of cylinder pressure, fuel systems, and really at this point, continued improvement in terms of catalytic conversion efficiency, advanced EGR, those kind of systems. And then aspiration, we were moving from a variable vane turbocharger all the way to an e-turbocharger. Mission controls pretty much and really improved closed loop towards the end, a bottoming cycle on waste heat recovery. Accessories, by the time you get to the end of this, the accessories are off of the engine. Weight is going to increase primarily due to the bottoming cycle, and the kind of peak efficiency we were expecting is 51 to 54%, albeit at a cost. Next chart. Improved tractor and trailer aerodynamics. Really important to try to keep the flow attached through various parts of the vehicle. The air gap, of course, is an important part between the trailer and the tractor and management of that. This tractor has some technology to do that. There are advances in terms of that people have advanced in terms of actually moving the trailer up, the fifth wheel pin up to reduce that gap. You can see the type of improvements that are needed on the trailer in terms of managing the flow underneath the trailer. So all that has to continue to improve, and we've included some of that in this analysis. Next slide, please. This gives you the analysis for the EU market segments. So again, remember where we were on the NAS, we were close to 50%, here we're less. And there's a number of reasons for that, which I'm going to explain in a minute. So the service market segment, we're talking about 35% improvement. Urban delivery, about 45. Let's go to the long haul, we're hovering in the 40. And again, what you can see, which was typical of the NAS, is that those market segments that are heavily stop and go duty cycle dominated, hybridization has the biggest effect. And those segments that spend a lot of time on highway, then aerodynamics is going to have the biggest effect. Lightweighting on transit buses has a huge effect, but it has an effect across the board too. Next slide, please. Why is the EU less in terms of its potential benefit than what we had in the NAS study? Well, there's a number of reasons. Lower speed. That reduces fuel savings by 5%, going from 105 to 90 kilometers per hour, using sort of the rule of thumb. Engine after treatment. Again, we did not have an SCR on this. The SCR is probably worth, in terms of increase in engine out NOx, something around 6% improvement, in my estimate. Also, transmission and driveline. The European incorporates an ATM, and the baseline that we used here. Plus, it's a 4x2 tractor configuration. That's an estimated fuel savings using the results we had in the NAS study of 7%. Finally, because of the configuration of the tractor and trailer in terms of number of tires and wheels, that estimates something like around 3% fuel savings. So the total difference, just using the same methodology we use to estimate what the benefits are, is about 19%. On the service side, the U.S. is a gasoline technology. EU is, here in Europe, you're primarily a downsized diesel engine already. That's a difference of about 24%. So let's pull up the next slide. So what I've shown you here is the potential GHG reduction comparing now the EU to the US. And you can see that, for example, in the service, the percent difference here is 23%. That's primarily due to the fact that it's gasoline on the US side, and it's a relatively inefficient gasoline on the US side in the baseline we use for the NAS study. Stoichiometric PDF type technology. And on the long haul, again, what you can see is that, again, it's about a 23% difference, and that is very comparable to the points I ticked off in the previous slide as why you should be different than that. Things like coaches are about the same, although the technology might be slightly different. Next slide, please. So let me make a couple of closing remarks. Like the US, the EU has potential to substantially reduce GHG emissions from heavy-duty vehicles. There's off-the-shelf diesel technology, in my opinion, exists with reasonable economics, although I haven't shown you that part. Secondly, the use of alternative fuels can also contribute to lower GHG emissions, although I didn't show you that. That's an important part. Total full fuel cycle, well-to-wheel analysis would indicate certain fuels like natural gas or electricity has the potential to substantially help reduce greenhouse gas emissions from this sector as well. For most heavy-duty segments, the powertrain improvement provides significant savings, not only in engine, but also in hybridization. Aerodynamics is going to be important for the long haul and duty cycles that have extended speed driving, and you need to do both the tractor and the trailer. And then finally, if you look at those segments that are using the most fuel, i.e. the most, and have the biggest impact on GHG emissions, you're talking about the long haul, the regional deliveries, service, and bus and coach segments. That accounts for 83% of the total HDV fuel consumption, greenhouse gas emissions in the EU, and therefore it will have the largest leverage. And by the way, many of those segments have like vehicles, long haul, regional delivery, articulated type tractor, trailer type vehicles dominate there. The service would be the smaller size vehicles, sort of in the mass production side of things, and of course the bus and coach are specialized vehicles to themselves. And then finally, just a thought from my perspective, even at the high fuel prices, although you did push technology in to the marketplace, if you're really going to be aggressive at this, you probably need some sort of regulation incentives to make it happen. So thank you very much for your attention.
Thank you, Mike.